Oracle performance. In this nugget, we'll discuss two different types of tuning. We have system tuning, and then we have individual SQL statement tuning. System tuning involves making sure that your parameters are set appropriately so you don't end up with memory swapping, or that your cache areas are large enough so things can stay in memory for easy access. So when we talk about system tuning, we'll first of all discuss how to size your redo logs so they're not switching every 2 seconds. We'll discuss a parameter that was introduced in 9i called PGA aggregate target. This is a replacement for about 4 other initialization parameters that we used in 8i and earlier. Then I'll show you the various tuning advisors. These are views that you can use that give you hints as to how large to make your memory structures. Now some of these are new to 9i, some of them were new to 10G. I'll also show you how to pin packages in memory. So if you've got some packages that are going to be executed over and over again, well, instead of having to load them over and over every time someone uses them, just pin them in memory. And then we'll look at a tool called StatsPack, which is commonly used for looking at the system as a whole. Basically what it does is it creates windows or snapshots of the state of your database every few minutes. And you can determine how often it's going to create that window. And then it can analyze what's going on during a certain window of time. Then for SQL tuning, we'll talk about how indexes can make your SQL statements run faster, and also the required Oracle optimizer to determine the execution path for your SQL statements. We'll also look at the explain plan tool so you can see what steps Oracle's going to take to execute a SQL statement without actually executing it. And I'll show you how to inject hints into your individual statements to send hints to the optimizer. And then the last thing we'll talk about are stored outlines, which is a way we can save the execution path of your SQL statement. Let's first of all talk about tuning our log files. A little bit of review here. Our buffer cache is a piece of memory in the SGA, and it just caches blocks from our data files. This buffer cache is actually populated by the server processes that are going to be reading data from the data files and then placing it in there. Well, every so often, this buffer cache has to get flushed out, and it's the task of the database writer to flush it out to disk. A checkpoint is when the database buffer is flushed to data files by the database writer, and there's also a process called the checkpoint process that updates the control file and data file headers. So you ask, what is going to trigger when this checkpoint occurs? Well, during a redo log switch, first of all, that's one scenario. Remember, in our SGA, we also have what we call the log buffer. That's a piece of memory that holds information about changes made to the database. And the log writer is going to write data from there to the redo logs. And remember, you have to have at least 2 groups of redo logs. These here are redo logs, and the reason why we have to have at least 2 is because it writes to these in a circular fashion. It's going to fill this one up, then it's going to fill this one up, and then it's going to then go back to the original one, fill that up, and so on. Oracle recommends that these redo log switches occur about every 20 or 30 minutes. If you look in your alert log file and you see that a log switch is happening every 1 minute or every 2 minutes, you're going to get a hit on performance. And so to alleviate that, you can increase the size of the redo logs. Let's assume that right now the size of my redo logs is 100 megabytes, and we find that every 10 minutes we're getting a switch. Well, I would go in and increase it to 200 megabytes. So once again, you can look in your alert log file to see when these log switches occurred. And it really is a good idea to go in there during a time of high activity. Because if you check the switch rate at 3 a.m., most likely it's going to be very different compared to, let's say, 12 in the afternoon. There's other things that can trigger a checkpoint as well. For example, a manual log switch. If you say alter system, switch log file, it's going to manually switch the log. You might want to do this if you want to force the information in these redo logs to get flushed to archived log files. If you have your archiving turned on, then every time a log switch occurs, then the information in a filled up log file is going to go to an archived log file. There are a couple initialization parameters that we used in 9i earlier, log checkpoint timeout and log checkpoint interval, and those affect how often this log buffer here is going to get flushed out to the redo logs. Log checkpoint timeout tells us the number of minutes to allow to pass before we flush out the log buffer to the redo logs. Log checkpoint interval specifies the number of blocks that get filled up here before it gets flushed out. Well, in 10G, we have a new parameter that we use instead that replaces these called fast start MTTR target. And that's going to be an integer number, and it specifies the number of seconds that we want our database to start back up in if we have to perform instance recovery. Well, what do these redo logs have to do with instance recovery? Well, let's say that we pull the plug on our database, we do a shutdown abort, and then when we start up our database again, our database is going to have to perform instance recovery. In other words, it's going to have to apply redo logs to the data files. The default value for this parameter is 900 seconds. If you want to make it larger, that's fine. Let's say that your fast start MTTR target is really, really small. Well, you're going to have a lot more log writer activity compared to a rather large value. My recommendation is just keeping this value set at the default of 900 seconds, and then go look in your alert log, and if you think that the checkpointing is too often or too far between, then go ahead and modify this parameter. Starting with Oracle 9i, we had a new initialization parameter called PGA aggregate target. Prior to having this parameter, we had to rely on 4 separate parameters to tune our program global area. For example, if you needed to specify sort memory, well, you would set the sort area size to a specific number. And then if you wanted to create hash joins, you'd have another parameter for doing that in memory. And then we had 2 more parameters dealing with bitmap indexes. Well, what was problematic about this was that if you allocated, let's say, 4 megs here, 4 megs here, 4 here, and 4 here, and you ended up not using some of these, then you end up just wasting memory. And so what we started to do in 9i is we just combined all of those parameters into one called the PGA aggregate target. And then Oracle takes care of how it's going to allocate that memory. Oracle's recommendation is to set the PGA aggregate target to 16% of the total physical memory for an online transaction processing environment, or 40% if you're in a data warehousing environment. If you're on a Unix or Linux operating system, you can look at the /proc/meminfo to find memory information. If you're on Windows, you can simply go into the control panel. Starting in Oracle 9i, we also have some really helpful views to give us advice on how we should tune specific memory structures. Be aware that for any of these views to work, you need to have your parameter statistics level set to either typical or all. It just says that, yes, we're creating statistics for activity on these different sections. By looking at any of these $V views, let's hone in on the $V shared pool advice. Basically, what Oracle does is it creates buckets. It creates a little histogram of activity, and it tells you, well, if you size your cache to this number, then this is the savings you're going to get. So it gives you a pretty wide spectrum, and then you can choose where you get the most savings. Let's make sure that our statistics level is set properly. Okay, just to show what our parameter is set to, I'll say show parameter statistics level. And good, it's set to typical. And then we'll do a describe on $V shared pool advice. And let's just pay attention to the shared pool size for estimate. This is like saying, if it's this size, then you're going to get your savings right here in the time saved. For example, if we say select shared pool size for estimate, we can also look at the factor, so shared pool size factor, and then the estimated time saved from $V shared pool advice. So we look at this first entry here and it says, okay, 60, and by the way, this is in megabytes, 60 megabytes. Well, the factor is 1, which means that's the current value. Our next entry is saying, okay, well, if it's 68 megabytes, we get a little bit more savings compared to 1843. So jumping to the last value here, if we size it to 124, our time saved is 1908. So I would actually size the shared pool to 124 up here. The shared pool size is something you can modify saying scope equals SP file. So you can say alter system, set shared pool size equals 124 megabytes, scope equals SP file. Now, for this change to stick, we have to shut down the database and then start back up again. Okay, now we can go ahead and start up. And then we can do a show parameter, shared pool size. And it's 124 megabytes. The other views work exactly the same way. They all have histograms with buckets. So PGA, once again, is to help you tune the PGA aggregate target. And then our DB cache advice is to size the database buffer cache. And if you're using Java at all with Oracle, then you'll want to set your Java pool size. Something that can also give Oracle performance hits is having an improperly tuned share pool or having objects go through the share pool too quickly, flushing it out. The shared pool is an area of memory in the SGA, and it's simply used to store compiled SQL and PL SQL code. It simply grabs the compiled code from the shared pool. If your developers have a package that they think they're going to use over and over again, well, it's best to peg it into memory. So we've got a package called dbms shared pool, and there's a procedure in there called keep, and you just feed it the package that you want to pin in memory. So in this example, we're assuming that the Scott schema has a package called pack1, and we are pinning this into memory. Let's go ahead and create that package, the dbms shared pool. So I'm already in my rdbms admin directory, and now I'll execute the dbms pool.sql. I don't have to add the .sql extension. Okay, and then we execute our prvt pool.plb. So now we're good to go. So now if we want to see which packages Scott owns, let's do a select distinct name from DBA source where owner equals Scott and type equals package. Okay, so Scott has a package called P1. So we'll go ahead and peg that into memory. So we'll say dbms shared pool dot keep scott.p1. The last part about system tuning I want to talk about is using Oracle StatsPack. StatsPack has been around since Oracle 8i, and it's a wonderful tool because it automates a lot of the process of gathering statistics. And you do that by running cat db-syn.sql as well as dbms-pool.sql if it hasn't already been run. And then the spcreate.sql is going to create a user called perfstat, which is going to be the user in charge of generating all of the snapshots and everything that has to do with this package. So basically, StatsPack is going to gather statistics on a regular basis. By default, it's going to be hourly. Oracle recommends making the snapshots about every 5 minutes, just so you can see what's going on in smaller intervals. So there you can see, memory structures, you can see wait events, things like that. So once you run these 3 setup scripts, then you call the spauto.sql to set up a job that creates the regularly occurring snapshots. And then after a little bit of time has passed by and you have a collection of snapshots, then you can run spreport, and it's going to ask you for a range of snapshots, and you can look at the performance between such and such time. So if you haven't already run these setup scripts, go ahead and do that now. This should only take a couple minutes. I already ran the first two earlier. I'll go ahead and run the SP create. This is a little bit of an interactive script because it's going to ask you for the perfstat password. And I'll go ahead and create a password for it. And it asks for the default table space. Well, right now it's saying that sysox is going to be the table space it's using. That's fine. We'll just hit enter. We'll stick with that default. And then the temporary table space, well, we only have one available one. That's temp. And then it goes ahead and it creates the perfstat user and everything else. Now, if you get some warnings in here, it's okay. It just means that some of these objects were already in there. Let's log back in. Let's go ahead and run spauto.sql to set up our job. And it tells us that the next time a snapshot is going to be taken will be at this date at 10 o'clock at night. It tells us up here what our job queue processes parameter is set to, because that needs to be set to something greater than 0 if you are running any jobs. I really recommend just automatically running StatsPack on a regular basis. Don't wait until something bad happens in your database, because in order to really see what should be happening, you need to collect data for when things are good, so you have some kind of comparison when you have performance hits. Let's move on to SQL tuning. We're going to talk about indexes, the optimizer, how to use explain plan and hints, as well as stored outlines. Let's talk about indexes. If I were to hand you a really huge dictionary and ask you to look up a word for me, well, how would you go about finding that word? Well, most likely you'd look in alphabetical order, and you could probably find it within a few seconds. What if we didn't have such a thing as alphabetical order? How would you find it? Well, you'd have to go page by page, and eventually you'd run across it. Well, we have the same kind of concept in Oracle. Oracle's got all sorts of indexes, but the most common one is the B-tree index. Let's take a look at this table on the right-hand side. Let's assume it's a rather large table, millions of records. And remember, the row ID is the unique identifier for each record in the table. Well, if I've got a query that says select star from person where last name equals Smith, and I have quite a few queries that have this kind of where clause where it's referencing last name, I might want to create an index on the last name column. And so the way it works is when we create the index, Oracle creates this tree structure that organizes all of the last names in alphabetical order. And the information in these leaves here in the index is not only the last name, but the row ID. So what happens is we look up this last name of Smith. It's A through Z. Now it's S through Z, and then this drills down to S through V. So in this leaf here, we would then find our Smith and the corresponding row ID or row IDs. It could be more than one person that's coming back. Now keep in mind that this index is only going to be used if we have the where last name equals. If our statement said select star from person where ID equals Smith, well, that last name index is not going to be used. We also have a type of index called a bitmap index, and this is used for low cardinality columns. What I mean by cardinality is the number of distinct values. For example, if we have a gender column and we have a possible value of M or F, well, that's really low cardinality. And so the way our bitmap indexes work is that for each distinct value, there's going to be a bitmap lookup with the row ID and a 1 for true and a 0 for false. So let's say you've got 1 million records in your table. Well, you'll have 1 million entries in each of these bitmaps. Be really careful with these bitmap indexes. If you're in an OLTP environment where you've got lots of inserts, updates, and deletes, it's really not a good idea to have a bitmap index, because updating this data is going to give you most likely a hit on performance. And the general rule with your B-tree indexes is that, of course, when you're inserting, updating, or deleting records, it will take a little bit longer compared to if you did not have an index. Imagine if you're trying to update the dictionary and insert new words into your dictionary. It would take a little bit longer to insert entries into the proper location instead of just appending it to the end. Makes sense, right? And one of the differences between our B-tree indexes and our bitmap indexes is that our B-tree indexes do not record null values. For example, if you've got a last name and the last name is null, well, that row ID is not recorded anywhere in here. Whereas with your bitmap indexes, null values are recorded. A more accurate picture of this diagram would be having this bitmap here for null values. If there were no records that had a null value, then this bitmap would not exist. Another thing you can do with your B-tree indexes is that you can have an index that's based on 2 or more columns. That's what we call a compound index. As long as at least one of those columns is referenced in the where clause, that index most likely will be used. For example, if I want to have an index that's a combination of last name and first name, that's fine. And so what's going to be stored in the index tree is the combination of the first name and the last name and the row ID. Well, to create an index, here's our official syntax. You're going to say create, index, and then the index name. Now, we already talked about bitmap indexes. We also have a type of index called a unique index, which is actually a subset of the B-tree index. The unique index is basically enforcing a rule that's saying that this particular column must have all unique values. And so if your existing data in the table for that column is not already unique and you try to create this unique index, it's not going to work because you already have data violating the rule. So you can either say create index, index name, create unique index, or create bitmap index. They all create different types of indexes. On, and then your table name, and in parentheses your comma-separated list of columns that you want the index to be on. Now make sure that these are columns that are referenced often in the where clause. So those two lines really are the only required lines, and then there's other optional parameters. For example, we can specify the no logging clause. This just means that while we are building our index, it's not going to generate any redo information. Well, this will be really beneficial performance-wise, especially if you've got a really large table. By saying no logging, it's going to give you a huge improvement in performance. The only drawback is that if you needed to perform database recovery for some reason, this index would need to be rebuilt. You can also tell Oracle to compress your indexes. For example, if you have a compound index on the last name and the first name in your person table, and you specify the compress option, it's just going to eliminate duplicate values. So if you have 1,000 Johnsons, well, by enabling key compression, you're reducing the redundancy of that name. Then we have reverse indexes. Now keep in mind when a B-tree index is created, it's storing the index column in ASCII order. Well, imagine that you've got a column that you're creating an index on, and it's a numeric column that you're auto-incrementing on. In other words, you're using sequences. So you have, let's say you've got numbers 1, 2, 3, 4, and so on. And then you get up into the higher numbers, 110, 111, 112. The more we add to our tree here, the more it's going to grow too heavily on one side on the tree. For example, we have quite a few numbers here that start with 1. So they'll be on one side of the tree, and after a while our tree will be imbalanced and it won't perform well. But if you specify the reverse keyword, you're just taking all these values and you're reversing the characters. So then we end up with 1, 2, 3, 4, and so on. And then we have 0, 1, 1, 1, 1, 1, 2, 1, 1, and you'll see how it's a little more balanced. So using these reverse indexes are really good to use on sequences and also on dates, because dates internally are really just stored as numbers and it starts with the year first. So you might have a bunch of entries for 2006. It would make more sense to start with the seconds value and then go to minutes and hours and so on, so the tree's more balanced. For performance, you can also give the parallel option. This parallel clause is telling Oracle to create the index faster using parallel processes. If you've got X number of CPUs on your machine, Oracle recommends using the parallel X minus 1 value. For example, here 7. If you've got 36 CPUs, then I would say parallel 35. You want to allow that extra CPU to do other things while Oracle's creating that index. How does Oracle know to even use our indexes? Well, it relies on what we call statistics, which need to be generated. So if you want to create the index and compute the statistics at the same time, then include this clause. We'll talk more about statistics in just a moment. We're going to create an index, a B-tree index, on one of Scott's tables. Let's do a quick describe on Scott's emp table. And we've decided that there's quite a few queries that are referencing the e-name. So we'd create an index on that. Say create index. Let's make it belong to Scott. And we'll call it emp name IDX on Scott's emp table. And it's the e-name column in particular. So our index is created. I'll show you in a moment how to tell if it's actually getting used or not. If this were a really large table, you might consider using the no logging or parallel clauses. Oracle's optimizer is the mechanism which allows Oracle to figure out what execution path to take on a SQL statement. For example, if you've got a SQL statement with a join on several tables, Oracle can decide which tables to use first as the join. Or if you're doing a select star from some table with a where clause, Oracle can decide whether or not to use an index on that table if you have the index set up. So long, long ago, the only optimizer available to us was the rule-based optimizer, which is based on some really complex rules. This is considered to be obsolete. We really don't use this anymore. And in 10G, the only place you can use rule optimization is within hints, which we'll discuss in a little bit. One of your initialization parameters is called optimizer mode. So yes, rule is one of those options, but we tend not to use that anymore. Another option that's available, but we tend not to use, is the choose option, which allows us to choose between the rule-based and the cost-based optimizer. Once again, we try not to use either of these. Now, the way the cost-based optimizer works is it's based on statistics that you either manually generate or you have a job generate on your tables, your partitions, your indexes. And these statistics include information such as how many rows are in your table, how many rows are in your indexes, what's the average byte length of each of those rows. And so then the optimizer can come along and say, oh, okay, you've got this table with an index on it, but there's only 5 records in your table. It really wouldn't make any sense to do an index lookup since it's so small. If your statistics are not up to date, then your optimizer is not going to behave like you want it to. Now, 2 other possible values for your optimizer mode is first rows and all rows. First rows tells Oracle to bring back the record set as fast as possible, and this is most likely used in an online transaction processing scenario where users need information back really fast, even if it uses a lot of resources. All rows is used more often in a data warehousing environment or in batch processing. It just tells the optimizer to take its time finding the data it needs and don't hog all of the resources on the machine. So a little while ago, when we created our index and we gave the option of compute statistics, well, that generated the statistics for our index. If you want to find out when the last time a table or an index has been analyzed, you can look at the last underscore analyzed column in the DBA tables or the DBA indexes view. For example, I can say select table name, last analyzed, from DBA tables where owner equals Scott. Now, if I'm logged on as a regular user, I would be querying the view called user underscore tables. Okay, so it looks like these were analyzed on these particular dates. If you find a null value in the last analyzed column, it just means it has never been analyzed. Well, how are you going to gather statistics? Well, the most common way is by using a package called DBMS stats. And there's all sorts of useful procedures in there. For example, you can gather statistics for just one table or one index, or you can specify a whole schema, or you can even say the whole database. A lot of my clients have had jobs that just gather statistics for the whole database at 2 in the morning, and it might take a couple hours if they're medium to large size databases. So we'd start off with the begin clause, remember to start off an anonymous PL SQL block. And then in this case, we're gathering our schema stats. So we say DBMS stats, gather schema stats. Then you say the owner name. So in this case, it's Scott. Make sure it's in capital letters. And then for options, you can say which statistics you want to generate. For example, when we say gather auto, that's the same thing as saying, look, generate statistics where there are no statistics at all, or where the statistics are stale. Stale statistics simply mean that the data has changed more than 10% since the last statistics gathering. You can also tell Oracle the sampling size, so it doesn't scan over everything in your table or index. It's just going to grab a percentage sampling. And if you say dbms stats.auto sample size, Oracle's going to decide how large that sampling is going to be. Usually it's between 5 and 20%. This is going to give you a pretty big increase in performance. And you can also say the degree of parallelism. So in this case, if we had 16 CPU on our machine, well, we take one away from that, which is 15. So here we'd have 15 parallel processes working on this statistics generation. Once again, increase in performance. So then we can go ahead and close this off, and it's been successfully completed. By setting this optimizer mode in your initialization file, you're actually setting it on the system level. You can also modify this on the session level or even on the statement level. For example, on your session level, you could say alter session, set optimizer mode equals, and then specify which mode you want. Or within a single select statement, you can say select, and this is where we can include hints. The way a hint works, it looks a lot like a comment. It starts off with a slash, star, plus, and then the hint name. So we could say first rows if we wanted to. The placement of the hint is pretty important. It always needs to be right after the first word, either select, insert, update, and so on, of your statement. So we could say select, there's our hint, star, from, and so on. Oracle provides hundreds of various hints that you can include in your SQL statements, and we're not going to get too detailed with that, but just be aware that there are hints out there, and if you want to find the detailed information, you can go to the official docs for Oracle's Performance Tuning Guide. How do you know for certain what execution path is going to be taken on a SQL statement? Well, like I mentioned, an explain plan is going to show that. When you explain the plan for a statement, the statement itself is not actually being run. Oracle's just showing us what path is going to be taken in order to run the statement. To produce the execution plan, you need to first of all create what we call the plan table. The plan table is just a regular table that is automatically populated when you explain the plan for a statement. To create this plan table, you have to go to your Oracle Home RDBMS admin directory and run the utlxplan.sql statement. That has to be run by a sysdba. In fact, I'm going to log in right now and execute this statement. So we'll say utlxplan, and our table has been created. So to populate the plan table, you just say explain plan for, and then the SQL statement that you want to have analyzed. You can optionally have a clause where you set the statement ID. That's just a unique identifier. So if you have more than one person at the same time doing an explain plan, there's a unique identifier for that explain plan. So I'm going to explain the plan for select star from scott.emp, where department number equals 10. Says it was explained. Let's do a select count from plan tables. See how many records are in there. You'll see that looks like there are 2 steps. The easiest way to see the data inside of that plan table is to do a select star from, and we're utilizing a pipeline function that, like I showed you earlier. So we say select star from table, and then we're going to utilize a package called dbms xplan, and it's got a function called display. Okay, I'll make this window a little bit larger for you. And we just pay attention to what's in here. Okay, so it did a full table access. Pay attention to the indentation here in the operation. We don't read this from top to bottom. We actually read from the most indented row to the least indented row. So it started off with a full table access, and that's it. Now it gives us the table name, the number of rows that were affected, the number of bytes that were read, and the cost is the cost in percent of CPU. So the higher the cost, the worse it is. Cost of 3, very, very low. I've seen some costs that are in the hundreds of thousands. And those statements, by the way, usually take a few hours. So you could see that we had a full table access. Let's delete from our plan table, clean that out again. Now let's do another explain plan. We'll say explain plan for select star from scott.emp where emp number is greater than 5,000. Once again, we can do our select star from table, use this pipeline function. I'll just go ahead and copy and paste it. Now our execution plan is a little different this time. We had an index range scan on the pkemp index. So it was looking for the primary keys of our employee table, and then it grabbed what it needed in the table. So it did not perform a full table access. It did a full index scan, grabbed the row IDs that it needed, then looked up those row IDs in the table. Very fast access. Now let me warn you, these are really, really simple examples. When you get to more complex examples where you have joins on 6 or 7 tables using materialized views, that can get very, very complex. Let's assume you're on a development database and you and your team have decided that, wow, we really like the way a lot of our SQL statements are performing and we want to kind of freeze dry them. We don't want any of the statistics to alter the way they're behaving. The way you can freeze an execution plan is with what we call a stored outline. After you create a stored outline for a particular SQL statement, then that execution plan will always be used for that statement. If you want to grant a regular user the ability to create stored outlines, you need to say grant create any outline to, and then the username. We'll do this for Scott. Now let's log in as Scott. And let's go ahead and freeze dry one of our execution paths. So we'll say create outline, and then we'll give it a name. I'll call mine my outline. On, and then our SQL query. So we'll say select star from emp where department number equals 10. And our outline's been created. Whenever you create an outline, it's going to belong to a category. And if you don't specify which category it belongs to what we call the default category. In fact, you can query your data dictionary view. If you're logged on as a regular user, you can say select name, comma, category. If you're logged in as the DBA, you would do a from DBA outlines. But here you would say from user outlines. You'll see here that my outline belongs to the default category. Now, just because we've created this stored outline doesn't mean that it's automatically going to be used. We have to set a couple session parameters. We have to first of all set query rewrite enabled to be true. This simply allows Oracle to rewrite the query according to what the stored outline says. So we can say alter session, set query rewrite enabled equals true. Okay, now the second thing we need to do is enable our particular category. So once again, we'll say alter session, set use stored outlines equals default. Now, within this session, when you issue that SQL statement that we defined for our stored outline, it's automatically going to be using the execution plan from earlier. What's really cool about these stored outlines is that once you create all your stored outlines, you can actually export them and then import them into your production database. So you don't have to do all that performance tuning in your production environment. Wrapping up this nugget, we covered two basic types of tuning. We've got system tuning or instance tuning, and we've got SQL tuning, which is on individual SQL statements. So for your system tuning, some of the things you can do are tune your log switches. For example, preventing your switches from happening, let's say, every 2 minutes, you don't want that much log writer activity. Instead, make sure it's right around every 20 or 30 minutes. We also covered that parameter, the fast start MTTR target, which can help tune how often the log buffer is going to get flushed out. Then we discussed our PGA aggregate target. That was the new parameter in 9i that replaced 4 other pieces of memory. For example, the sort area size. Then we have our tuning advisors. We've got our $DB cache advice, $shared pool advice, Java pool advice. You can also pin packages in memory with your DBMS shared pool .keep procedure. So this prevents your packages from going into memory and then getting flushed out and then getting parsed again. You can just pin them in there. And then we talked about StatsPack, which takes snapshots of our system on regular intervals, and then we can use the SP_create report that tells us general information about what's been going on the system. Then for our SQL tuning, we've got indexes. Those are the database objects that we create on table columns, and it helps the column lookups occur faster if they're referenced in a where clause. Kind of like looking something up in the index of a book. It allows you to look something up quicker. We also have our Oracle Optimizer. We have the old style rule-based and then the new style cost-based optimizer, which is based on statistics that you have to generate or have a job automatically generate. Explain plan shows the plan that the optimizer is going to take to execute your code without actually executing it. And then hints are pieces of code that we can inject into our SQL statements to give the optimizer a hint as to what you really want to happen. There's no guarantee that it's going to happen, but it nudges it in the right direction. And then we talked about stored outlines, which is a way that you can freeze the execution plan of your SQL statement. Well, I hope this has been informative for you, and I'd like to thank you for viewing.